So this was discussed in the last class. This is the list of heavier baryons other than protons and neutrons and their decay modes. And this was the list of mesons, heavier mesons and their decay modes. And this was some other table where the strange particles are produced in pairs from scattering experiment. And these are some processes which are not seen in the universe, though baryon number, lepton number, and charge are individually conserved in all these interactions. Okay, and we discussed that this table D tells you that you need a different new quantum number to explain non-occurrence of these processes. Okay, and we have also seen that these heavier baryons decay by interactions whose timescales are of this order, which means they mostly decay by weak interactions. Some decay by electromagnetic interaction where gamma is produced. Here also these heavier mesons, they decay by weak interactions, but the strange particles are produced in pairs, and also their time scale of these interactions are 10 to the power minus 23 second, which is the strongest of all the interactions. So these are strong interactions, but though the strange particles are not produced singly in these interactions, they're always produced in pairs. These interactions never happen in nature, though these quantities are conserved. Okay, so all these discussions, all these conclusions which you can draw from these four tables, let me summarize it here. So we are discussing about heavier baryons and heavier mesons, and from above four tables we see that I discussed already, but I write it here in a concise way. Strange particles decay by weak interactions, okay, because their lifetime is 10 to the power minus 10 second, which is the characteristic time scale of weak interactions. In some cases by electromagnetic interactions too. Okay, so strange particles decay mostly by weak interaction, in some cases by electromagnetic interaction. But in case of decay by electromagnetic interaction, photon is always emitted as one of the decay products. Okay, strange particles never decay by strong interactions. That we see at least from this table. The first two tables. These are strange particles. The strange particles I mark by heavier baryons and heavier mesons, I mark by red color. Okay, so only one of them here I see that they decay by electromagnetic interaction. Their time scale is different. But in electromagnetic interaction, gamma should be present. Not in all electromagnetic interactions, but in the decay of strange particles, those electromagnetic decays, gamma should be one of the products. Clear? Second point is, when strange particles are produced in scattering, that is this table, they are scattering, not decay. When strange particles are produced in scattering, they are always produced in pairs. A strange particle may be produced singly only in the decay of another strange particles. So those strange particles are produced in pairs, but in the decay you can see that these strange particles here, they are produced in the final state, that is one single strange particles. But this can happen only if this strange particle is produced from the decay of another strange particle. So anyway, there are two strange particles involved in this decay. Okay. Now the third point is that strange particles are produced in strong interaction, except when it is produced from the decay of a strange particle, which is a weak odd electromagnetic process. Okay. So strange particles are produced in strong interactions. These are strong interactions. They can also be produced by electromagnetic or weak interactions only if They are produced by decay of these strange particles. But whenever strange particles are produced from scattering, they are always strong interactions. So these are three main observations you can make out of the list of these tables. Okay. Now, to realize these three observations, this 1, 2, and 3, in terms of a quantum number, we introduce a quantum number S called strangeness, which should be assigned for different particles in such a way that we adopt this principle that strangeness is conserved in strong interaction and strangeness is violated in weak interactions. Okay. So looking at this table, if you carefully look at this table and these observations, then you will see that a new quantum number is needed, but that quantum number cannot be conserved in all interactions because this table does not show that. For that, this table differentiates between different types of interactions, strong, electromagnetic, and weak. And in strong interactions, you can see that. So we introduce the concept of this quantum number strangeness in such a way that it is conserved in strong interactions, it is violated in weak interactions. Okay, so let us verify whether this, if I choose to assign strangeness in this way, let's verify what happens to these tables. So let's come to the table C earlier, which is the production channel of strange particles, and all these interactions are, because of this time scale, are strong interactions. Now we assign strangeness quantum number values to the particles k, sigma, and this k, sigma, lambda. These particles are there. But remember, we have to assign strangeness such a way that it is conserved in strong interaction. That means in all this interaction, strangeness should be conserved. So keeping this in mind, we just manipulate and assign the values of k's, these particles, in this way. So k plus and k0, these two, k plus and k0 have +1 strangeness. If I assign it, initialize it in this way, so that their antiparticles will automatically have -1 strangeness. There is no need to assign. They are dependent. And this sigma, all this sigma, let's call sigma plus, sigma 0, sigma minus, they are assigned a strangeness number -1. This gamma 0, sorry, this lambda 0 is also assigned as strangeness number -1. We initialize the first strangeness to particles in this way. And the other particles, proton, neutron, this lighter baryons and lighter mesons, they are assigned 0, and all other particles have 0 strangeness to start with. So only non-zero strangeness are this. If we assign this way, then you can clearly verify that in this process, strangeness is conserved for all these processes, because see, k plus has +1, sigma minus has -1. Okay, so +1, -1, 0. This side is 0. K0 and sigma 0. K0 is again +1. Sigma 0 is again -1. So 1 -1, 0. K0 is again +1. Lambda 0 is again -1. That's why lambda 0 is assigned -1 to make it 0. So we assign this initial strangenesses first this way, that they are conserved in these interactions. Okay, and we will check now that since while assigning this strangeness, we stick to this rule that it is conserved in strong interaction and violated in weak interaction. I forgot to write it here that strangeness is conserved in strong and electromagnetic interactions. It is only violated in weak interactions. So later I have written it, but here I forgot to write. So take that. So strong interactions and electromagnetic interactions. they are conserved. Now you can check with this strangeness, verify that strangeness is not conserved in the interaction channels listed in table D, which does not occur in nature. This is the same table D I wrote earlier, where the strange particles are produced singly and which are not observed in nature, though baryon number, lepton number, charge are individually conserved. Now you see that since they have non-zero strangeness, only K, sigma, and lambda, and you can obviously check that in these reactions there is only one such strange particles here, and these particles are not have strangeness 0. So obviously these particles have either strangeness 1 or -1. So strangeness is not conserved in this process. So that non-occurrence of this set of reactions we can explain by non-conservation of strangeness. Okay, so these processes do not occur because strangeness is not conserved here. And these are, okay. Now, that does not mean if strangeness is not conserved, a process will not happen. As we have seen that strangeness is violated in weak interaction. So if you look at a weak interaction process, the strangeness number should be such that strangeness must be violated in those weak interaction. That an interaction is weak, you can first check by checking its time scale. You can measure the time scale of occurrence of this interaction and check whether it is weak or not. And then you can check whether this strangeness is conserved or not, and you will verify that for all interactions which is weak interaction, we will see that strangeness is violated if we assume this assignment of strangeness, initial assignment of strangeness, non-zero strangeness. Okay, so let us do that. But before that, let's include something more. So this is again, let us write this table C again. This table C is again this table where strangeness is produced, strange particles are produced from scattering experiments in pairs. Okay, so I am again writing this table C now, but introducing some new particles. I added some new particles here also. So these are the 3 interactions listed there earlier. Now we have added another 2 channels where some particle eta of this mass and this mass are produced. Okay, so all this time scale is saved, 10 to the power -3. So all these are strong interaction. This is the production channel. And since this is a strong interaction, strangeness has to be conserved here. Okay, now this demands that K minus I'm sorry, there is something wrong here. Sorry. Something is wrong here, I think. What is wrong? Oh, because pi minus. Sorry. Okay. So this should not be K. This is P plus pi minus. I will correct it. Sorry. All these first three are P plus pi minus. So these are the same 3 interactions of table C which occurs in nature, production channels in nature. Okay. I'm sorry, just a minute. I'm sorry. No, this is not pi minus. So this is, okay, so look at this channel C. These are the production table C. These are the production channel of these strange particles. And I give some more production channels of strange particles. Sorry, these are not wrong. All these are correct. So sorry. Okay. Now, so where I introduced some new particles, all these particles, which are again some you can check from the above list that they are some heavier baryons. Okay. Now we have already assigned strangeness to this K thing and this K particles. We have strangeness K. We have this strangeness that K plus has +1, K minus have -1, K0, K bar has +-1, and these new particles here are this chi0, chi minus, omega minus, like that. So that since all these interactions are strong interactions, strangeness should be conserved in this interaction. And from this initialization of strangeness of K0 and K plus K minus, and from the fact that strangeness is conserved, we can calculate the strangeness of the newly introduced particles. Okay, because strangeness has to be conserved. First, we can check that all the newly introduced particles have baryon number 1 because baryon number is anyway conserved in all interactions. So P has a baryon number 1, K is a meson, has a baryon number 0, K0 is a meson, has a baryon number 0. So this should have a baryon number 1. So this chi0 is a particle with baryon number 1. So that means there is a new baryon. Similarly, chi minus is also a baryon because K plus, K minus all have baryon number 0. Similarly, this omega minus, this is a new particle I am talking about. It has a mass of this. This is produced in this strong interactions. It is again having a baryon number +1 because proton has +1. All these K's at 0. So this should be a baryon number +1. So it should have a baryon number +1. Now there are some more particles, there are some eta particles and eta prime particles. They have these masses. Check that. Sorry, this should be eta plus pi. Now this is an error. Eta plus pi 0. Is it so? Is it so? Sorry. No, it's correct. So P plus pi minus gives you, this is N, this is not eta, neutron plus eta, and P plus P gives you this interaction. And you can check also from these interactions that this eta in this interaction should have a baryon number 0. Clear? Because proton and neutron each carry baryon number 1. Pi minus has a baryon number 0. So eta should be a baryon number 0. Similarly, this eta prime should also have a baryon number 0 because these 2 p's here and 2 p's here. In this final state, they have this baryon number 1. So the bottom line is all these newly introduced particles, K plus this sigma, this chi particles and this omega particle, they are baryons, and this eta and eta prime, these particles in the last two equations, they are mesons because they have baryon number 0. Lepton number is 0 for all these particles. Okay. Now look at try to assign the strangeness of these particles. From the fact that strangeness is conserved in this interaction because they are strong, and strangeness is assigned already for these K particles. If for the first equation, if strangeness, so if you remember, the strangeness of K minus and K0, what is that? Strangeness of K minus and K0 both have -1 strangeness. Okay, that means sorry, it's not -1. K minus have -1, K0 has +1. So K minus have -1, K0 have +1. Okay. So come here. So proton has 0 strangeness. This has -1 strangeness. This has +1 strangeness. Okay. And if we want, strangeness has to be conserved in this reaction because it is strong interaction by our rule of assignment of strangeness. That means this sigma, this chi0 should have a strangeness number how much? -2. Clear? Then both side -1. Similarly, in the next equation, this has -1. Same, the k plus is also +1. So this is also -2. Okay. So strangeness of chi minus and chi0 is -2. This is chi0. Now come to the third equation. Third equation is again a new particle, this omega minus, and you can check that k minus have a strangeness -1. K plus and K minus both have strangeness +1. Okay. Both have strangeness +1. So if strangeness has to be conserved, this omega minus should have a strangeness equal to -3, because -3 + 1 + 1 is -1. Clear? So omega will have a strangeness of -3. So looking at these new production channels of these strange particles, we find that omega has a strangeness -3, and you can easily check that these interactions p and pi both have zero strangeness, n also, so eta should be a particle of zero strangeness. Similarly, in this reaction, eta prime, their strangeness should be 0, because these protons are zero strangeness particles. So eta and eta prime are zero strangeness particles. So is this clear?
Yes, sir.
So if you actually I am seeing that someone is writing some questions in the chat, because when I teach I don't look at the chat. So if you have any questions, you can directly stop me and ask in words. Okay, at the end. So this is how. So the bottom line is, or the summary is, the strangeness we assign in such a way that it is conserved for strong reactions and validated weak interactions. If we introduce it in this way, then we will see that strangeness assignments for these particles are like this, and also for these new particles are like this. Yeah. So we need a different. So what this strangeness quantum number does, it also tells you which reaction will happen or not, but it also tells you more which interaction will happen by weak interaction or which by strong interaction. Yeah. So it is introduced in that way. It is conserved in strong and electromagnetic interaction. It is not conserved in weak interaction. So if you see a strangeness is not conserved in any interaction, then if that reaction happens, then you can say that that is a weak interaction. Clear? If you see that there is a strong interaction channel in all possible ways, but strangeness is not being conserved in that reaction, then that reaction will not happen, because strangeness has to be conserved in strong interaction. So to summarize, let's update the strangeness number assignment table. I put all these particles together. So you look at it, that K0, K plus have strangeness +1. Their baryon numbers are also 0. So they are mesons. Their baryon number is 0. Lepton number is 0 for all particles. We are not discussing about leptons anyway. So they are mesons, but they are strange particles. Now we see there's eta and eta prime particles. Their strangeness is also 0, and they are also baryon. Sorry, their baryon number is also 0, so they are meson. But their strangeness is 0. Clear? These particles, their strangeness is like -1, -1, -2, -3. These two are very important. So this is the only quantum number which take more values other than +1, -1 or 0. So its strangeness takes -2 for this and -3 for this. Baryon number is again 1 for all these particles. You can check from all these interactions. And so they are baryons and strange particles. Okay. And these protons, they are lightest baryons and mesons. So they have strangeness 0, and proton is a proton, neutron are baryons, and pions are lightest mesons. So only thing is not that though eta here, eta is a meson, okay, but it is not the lightest meson. Lightest mesons are pi plus, pi 0, pi minus. Though eta is not a lightest meson, but still it has a strangeness 0. Now we redefine the definition of strangeness. Earlier we defined strangeness as strange particles as particles which are different from lighter baryons or lighter mesons. Heavier baryons and heavier mesons, that definition we take as a primitive definition of strange particles. But from now on, we adopt a new modern definition. Any particle which has a non-zero strangeness is called as strange particles. And we discard the initial previous definition, that primitive definition, we discard it, that any heavier baryon should be strange particles, because we found out that eta are heavier baryons and they are not strange particles. Their strangeness is 0. So this better definition is to use the definition that non-zero strangeness particles are strange particles. So in this list of baryons and mesons, the red colored particles are only strange particles because they have non-zero strangeness. Clear? So we redefined, or we updated the very definition of strangeness by introducing by defining it the particle which have non-zero strangeness. Like lepton, we called a lepton is a lepton which has a non-zero lepton number. A particle is called baryon when it has a non-zero baryon number. Similarly, a particle is called a strange particle whether it is it has non-zero strangeness. So, but initial definitions are useful to for the beginners. Okay, but once you come out new particles which violates the initial definition, then you have to discard the initial definition. But you already found in that course that there are some more modern definition you can take up by introducing the number strangeness, because strangeness has non-zero values only for those strange particles. Here. Just a minute. Do you have any questions? Now, if we now have this strangeness assigned for so many particles, now we revisit the earlier table of decay and verify that strangeness is not conserved. I have stated this, but let's verify. Strangeness is not conserved in the observed decay channels of strange particles which happen by weak interaction. So strange particles decay by weak interactions, that we have seen, but and strangeness should be violated in weak interaction. So you can check from this above assignment of strangeness that strangeness is anyway violated in weak interaction. But note that red particles carry only non-zero strangeness. So this is the same table, but with more. I included all the baryons here, include protons and neutrons. So this you can see that there is one strange particle in these interactions. So strangeness is violated in this interaction because this has one strangeness, this has 0, this has 1, this is 0. In this interaction, both particles are strange particles, and sigma 0 and gamma 0. What is their strangeness? Let's see. What is sigma 0? Sigma 0 is minus 1, and lambda 0 is minus 1. So both sigma 0 and lambda 0 are minus 1. So both in this interaction, both are minus 1. So strangeness is not violated here, but this is not a weak interaction. This is an electromagnetic interaction. So this proves that in electromagnetic interaction, strangeness is conserved. Okay, it's a verification. Similarly, here, the strangeness is violated because only one strange decay. Here, you know that these chi particles have strangeness -2, and these particles have strangeness -1. So strangeness is violated, and these are weak interactions. Okay. Now this omega particle has a strangeness -3, and you can check that these two will not add up to -3, and these are -2. So strangeness is violated in this decay also, and this is a weak interaction. So in all, you verify that in all weak interactions, strangeness is our assigned strangeness, values of strangeness are such that in all weak interactions, they are violated. In electromagnetic interaction, anyway, they are conserved. And we have already checked that they are conserved in strong interactions. Similarly, for mesons, you can also check for the meson table that strangeness is violated in the weak interaction. So K minus dk is weak interaction, strangeness is violated. This is, here it is violated, here it is violated. Here it is conserved, they are electromagnetic decays, because both sides are 0. Okay, so you can check, these are the I again repeated this table, only the non-zero values of strangeness are marked here. Okay, actually I typed it, so there may be some errors. If you encounter the errors, please send me a mail that this is an error. But the errors you can only find if you read this and very thoroughly and understand whatever I am saying. Is this clear? This is how strangeness are introduced, that it is conserved in strong interaction, violated in weak interaction, and also conserved in electromagnetic interaction. Okay, and all these tables are there, you can verify this. And the tables are the experimental observations or non-observations. All these particles in the tables has been experimentally observed. Okay, let's summarize here what we discussed so far, so that we can capture the last 2 days class in one slide. The bottom line points that subatomic particles, based on their nature of interactions, may be classified as leptons, baryons, and mesons. Okay, baryons and mesons are together called hadrons. You know this. Now leptons carry non-zero lepton numbers and zero baryon number. This is also well known. Now baryons carry non-zero baryon number but zero lepton number. Mesons carry zero baryon number, zero lepton number. Okay. Some of the hadrons, that means baryons and mesons, carry non-zero strangeness. All hadrons do not carry strangeness. Some hadrons carry non-zero strangeness. Others are zero strangeness, like proton, neutron, pions, eta particles. They are zero strange particles. So these non-zero strangeness particles are called strange particles. All the interactions between subatomic particles can be classified into 3 categories depending on their strength of the interaction. They are weak, electromagnetic, and strong. This is in order of increasing interaction strength or decreasing time scale of occurrence. Okay. There is a 4th kind of interaction. This is I am discussing at this here. I have not discussed it earlier, but this is obvious. This 4th kind of interaction, which is gravity, it has negligible strength with respect to other 3 interaction when considered between subatomic particles. So if you want to find out, if you find the gravitational interaction between 2 electrons or proton or electrons or any strange particles like the subatomic particles, the gravitational interaction is much less than, negligible than the other 3 interactions. So in the study of elementary particle physics, we do not take gravity into account. The model of model of particle physics, the model by which we understand or which lists our understandings of the particle physics is called standard model of particle physics. We will learn it slowly. In this model, gravity is excluded when one talks about interactions between the particles. Here, so only 3 interactions are relevant for interparticle interactions in the subatomic level, at the subatomic level. The 7th point is the baryon number, the lepton numbers, and the electric charge, along with spin, energy, and momentum, are always conserved in all interactions that happen in nature. In interactions channels that never happen in nature, at least one of the conservations must be violated. Okay. Strangeness is a special kind of quantum number which is conserved only for strong interaction and electromagnetic interactions, but not in weak interactions. Okay, so this is how, I mean, we just verified this for all these tables I showed you, all the particle tables I showed you here. Okay. So if you have any questions, you can ask me now. I am stopping. I will start something. New, interesting things. But before that, up to this introduction of strangeness, to introduce the idea of strangeness, we needed to introduce see the pattern of heavier baryons and heavier mesons. Okay, from that we introduced the idea of strangeness and got. So if remember, if we have this list, this list of 8 points, this list of 8 points basically summarizes all the nature of interactions of all the particles. You don't need to know from these tables, from all these points, you can write down an interaction and can check whether this interaction happens in nature or not. Or you can check whether that interaction is strong or weak. Okay. So these are the extractions of the principles embedded in the dynamics and interactions of the elementary particles in words. Clear? Is it clear to everybody?
Yes, sir.
Yes.
Or you are so silent that I am frightened whether anything. Is it going above your head or too below your head? You are too above.
Sir, it's neither too above nor too below.
Okay. So, but you have to be very careful while. So now you can feel that how much patience one needs to extract these points, because you have to check so many interactions. You have to check which interactions happen, which does not, which is strong, which is weak, and then on that basis you have to classify the particles. Okay, but the come out is this. Okay, let me take a break for a minute and then I will start again. Hello. So, to be frank, uh, have you studied any topic of physics like this before, where there are no mathematical calculations?
No.
Because there are no, even you don't have to differentiate anything, no need to integrate anything. Only thing you have to add, you have to know this addition and subtraction, and that too simple numbers like 0, 1, 2, 3 for this checking these conservation laws. All these are pure logic based on, and without help, I mean, simple logic without taking the help of mathematics. Okay, any complicated mathematics. It is just experimental observations. Looking at that experimental observations, uh, um, I am I am scrutinizing these results and classifying and discovering the new quantum numbers in such a way that their conservation or non-conservation will dictate the occurrence or non-occurrence of a reaction. And in that course, we found out there are something more interesting quantum numbers called strangeness quantum numbers, which also differentiates between different types of interactions. Okay, so this summary here in this page, or whatever these conclusions we are drawing in this course, are basically uh, uh, simple statements extracting from the raw experimental data. Okay, you are purifying this raw data to, I mean, this raw data to make it transform in normal English language. Okay, so you can tell that the raw data as the machine language, which only machine nature understands, and this is this user-friendly language, this normal English language which user gives inputs. Okay, so you see on your screen, computer screen, only English letters or these English commands like that, in which has English meanings. But in this, inside the computer, it works like 0 and 1. Okay, so it's like that. Anyway, now there are more. I mean, so we are gradually entering into a forest, or in a, it's better to say it this way, we are going to a zoological garden or a zoo. This is called particle zoo. When we have not gone to the zoo, we used to live at our home. Then we have only domestic animals around us, like cats, dogs, birds, I mean, cows, like that. We don't know them. As we enter into the zoo, we see new types of animals which we have not seen in our residence, in our place, in our locality. But we are seeing new types of animals. But though new, we can match them with our previous background knowledge that this animal, though it is different, but it looks almost something like a dog. This animal looks, this is a bird. This falls to the class of snakes, like that. So you are so the number of particles in each of your class is increasing. Okay, birds, animals, mammals, insects, which we found only some elementary such particles, or some easily available particles at your home. But when you go to the zoo, you see much more particles, and you try to classify them based on your previous background. Once you classify a sort of particles, then you can enter into the more deeper forest, or a more I mean, into the more erotic island of the erotic places of the zoo, and can find more erotic animals. Okay, and then you can compare with your previous set, which is already been increased so far. Okay, so this is how you probe the zoo of particles. Okay, Now, if you have already given a careful look at the lifetimes of all the particles here, you will see most of the lifetimes of the particles mentioned here or in all these tables, previous tables, they are of the order of 10 to the power minus 8 second, 10 to the power minus 10 second, 11 second. Some has very high lifetime, 10 to the power minus 20, but no particles have lifetime like 10 to the power minus 23 second or minus 24 second, too short lifetimes. Okay, so let's discuss about these particles. So there exist, we will see gradually in this particle zoo, there are particles which are very short lived. We will explain slowly what do you mean by very short, what that very short lived. To roughly very short lived means their lifetime is order of 10 to the power minus 23 second or 24 second, like that. Now, we know that if a stable particle or if it is charged, it is created in a collision, then we can see its track clear in a detector and we can detect this particle. Even for unstable particles, we can see the tracks because pion, muons are all unstable particles, but they have lifetime of the order of 10 to the power minus 8 second or 10 to the power minus 6 second or minus 10 second, okay, like this. So these particles which have a lifetime of the order of 10 to the power minus 8 second, even if they travel at this speed close to the speed of light, even if they are very relativistic, ultra relativistic, with this speed, this is the time of this is the lifetime. Okay, this is, so any particle lives for this much time. So these pions and muons from their production point to their decay point, okay, from the point of their birth and to the point of their death, this time gap is 10 to the power minus 8 second. Within this time, with the velocity of light, they can travel few meters. Okay, and few meters is a length which you can easily resolve with your length measurement tools. Okay. But this is not the case when the lifetime is much smaller. So if a hadron, like hadron means either baryons or mesons, we are not talking about leptons. We know that leptons decay, leptons are this, muon is a lepton, tau is a lepton. Their lifetime is of the order of 10 to the power minus 10 or 11 seconds. So they do not decay, they decay by weak interactions. If hadrons decay by strong interactions or even by electromagnetic interaction, it will have much shorter lifetime because strong interaction, this is the strong interaction time scale. And this is the weak interaction, electromagnetic interaction time scale. If the lifetime of the particle is this, then even if the, say for this is an estimate, if a lifetime of the particle is this, with this lifetime, a particle can only move about, this is 10 to the power minus 10, minus 9 to minus 10 centimeter in their entire lifetime. Clear? Because this lifetime is so small, you multiply it by the velocity of light, you will find that the distance traveled by these particles during their lifetime is this. And this dimension is of the order, so this is the dimension of a nucleus. So it is not detectable. This track of this length will not be detectable is not resolvable experimentally. Here. So if there exists particle in nature which has this much of lifetime, they can't be detected by just looking at their tracks, if they're charged particles anyway. Then how to detect and study properties of such short-lived particles? Okay. There is another name for the short-lived particles. That is called resonance. They are called resonance particles. Why they are called resonance, we will see soon. Okay. So what is a resonance particle or such short-lived particles, if you measure a differential cross section, because in any particle physics experiment, the first thing you measure is the differential cross section, scattering cross section of any process, or total scattering cross section of any process as you want to explode. Now, whenever you see the differential cross section of a process, differential cross section is d sigma dE. That means how much scattering is occurring per unit energy. That is the differential cross section. When it is integrated over dE, it gives you the total cross section. So differential cross section with energy. You plot this function. This is an experimental plot of some differential cross section of some process against energy. This is an actual experimental plot. If you do the plot, you will see this. The plot can be different for different interactions, but for any type of interactions, you can see the plot has certain features. In some region, the plot has its own characteristics, but at some point of time, at some values of energy, the plot gets abrupt rise or spikes. I mean, not a single. I mean, like this hikes. Okay. So these spikes are called resonances. These are the definition of resonances. So what does it physically mean? We will understand now. The bottom line is, whenever you measure and cross-section of an experiment, differential cross-section of any process, and plot it as a function of energy, suppose A plus B going to C plus D, you are measuring how many part A and B are scattered with as a function of energy of A and B, total energy of A and B, say. And you plot this total energy versus cross-section. You will find that the number of particles scattered changes with energy or slowly. Suddenly, it gives a sharp bump, and then again it follows some characteristic path, and then again bump, and like this. Okay, number of bumps depends on which scattering you are looking at, and these bumps are referred as resonances. I will call these bumps as resonances. Let's understand how it is occurred in this cross section. So explanation for this occurrence of resonances. What is the explanation for these peaks? Okay. So let's consider a scattering A plus B going to C plus D. Okay. So this is initial state. This is final state. Let's say A plus B. This initial state, we are observing it in a center of mass frame, so that A and B are moving in opposite directions, and their total energy is ECM. So ECM is root over PS square plus MS square plus root over PB square plus NB square, where PA and PB are of opposite sign. So PS square and PB square are same. Okay, so this is the center of mass energy. So you can do it in any frame, but let's do it in center of mass frame. Okay, so let's go slowly. Consider an observed interaction A plus B going to C plus D. Let's choose center of momentum frame for this system. Let the total energy of the initial state of the frame is ECM. Suppose the experiment is this. Suppose we gradually increase the total energy of the system. That means we gradually increase if A is thrown at B, we gradually increase the energy of A. Or if A and B are projected towards each other, we can gradually increase energy of both, so that which will increase the total energy of the system. We gradually increase it and count the number of scattering delta N taking place for each energy window between ECM and E delta CM. Okay, so we fix ECM at some value and then change it by a delta ECM and count how many particles get scattered for this energy. So we get delta N by delta E, which is a measure of delta sigma by delta E, scattering cross section. That is how we plot this curve, delta sigma by delta E, or this curve. Okay. Now, as the energy increases, the cross-section should change. Why the cross-section should change? The number of scattering should change because it depends on the intrinsic nature of the dynamics of the interaction, which we have not studied so far. You will study it in your theory course, quantum field theory course, quantum field theory 2 courses. But there must be some, but this is an intuition, there must be some mechanics involved in this scattering, because of which number of particles scattered depends on energy of the incident particles. Okay. In course of, okay, so this is normal scattering. So if you change E, you see that differential cross section changes like this. It may changes like in different ways. I have drawn just one curve. Okay. Now read this very carefully, or follow me carefully. In course of increasing the energy, if we reach a point when the total energy ECM is equal to mass of a short-lived unstable intermediate particle, say delta, that means if nature allows existence of any particle delta whose mass is, say, m. Okay, so delta, so the rest mass is m, so its rest mass energy is mc square. We are using natural units, so mass is in the unit of energy. Now we are increasing the value of ECM. So we are moving along this side. When ECM becomes equal to m, what happens? ECM becomes equal to m, that means this total energy, from this total energy ECM, total energy is, earlier it was spending, this total energy was spending itself to produce the particles C and D. Okay. Now this total energy is now spending to form this particle delta, because delta has the mass of, because mass energy conservation is respected here. When ECM is equal to the mass of this particle, then delta particle can be produced at rest. Delta particle can be created at rest here. So delta particle is created, can be created from this particle. Now, if this delta particle is a long-lived particle, then we will not see, we will not observe this state as the final state. We will observe only this A plus B going to delta. That is okay. But if it is very short-lived and it happens that it decays to this particle C and D. Suppose it is so short-lived that it lives for 10 to the power minus 23 seconds. Then it decays within the moment it is produced at rest, you are increasing the energy. When the energy just matches with the particle M, this particle M will be produced at rest. You will have no momentum because your energy, total energy of the initial state becomes equal to the total rest mass energy. There is no extra energy to give the momentum to the particle. Clear? Now, before you increase the energy, the particle is so short-lived that it decreases. So this particle can't move. Okay, this particle gets no time to move so that it can produce any track. It just decays to again C and D. Now, if such happens, if such is this is the case, then what you will see is that if there was no such particles produced, you could have seen this. But if this delta particle is produced as an intermediate state particle, which decays very soon or in almost instantly as it is produced, then you will see a peak in the cross section. Why a peak? Because cross section is a measure of number of scatterings. Because as it was falling, the moment it reaches the value m, the more and more particles will be involved in producing the particles delta. So if you count the number of scattering by counting the number of particles A and B present at any energy, then suddenly we will found that more and more A and B are getting consumed, getting lost from your system. And therefore the total number of scattering will increase, because as more and more A and B particles are get consumed, but that is your measure of number of scattering. So number of scattering is total number of A and B thrown minus number of A and B not reaching the detector. That is the measure of number of scattering. So since more and more A and B are getting involved to produce this particle M at this energy, so at this energy you will suddenly see that more and more particles are vanishing from your system, A and B particles, so which will increase the number of interactions. And when you increase energy further, and the moment it is produced, it decays. Okay, so again it produces C and D. Okay, again it produces C and D, but there are, you have already increased your energy now. Now that energy momentum conservation equality condition, that E equal to M, is now lost. Now there will be no A and B will not be consumed to produce this particle. Therefore, the number of scattering will reduce and follow its natural characteristic path. Yeah. So whenever there is an intermediate state, there will be a rise in the cross section. Do you follow this? Can you follow this? If you can't follow, please tell me.
Yes, sir.
Okay. Now, there's one thing, important thing, that later you read these words, sentences line by line, you will understand. But you see that this equality is called resonance. Okay, so so when E equal to M, suddenly the number of interactions increase, but E equal to M is a particular value. That means it should have been a linear spike instead of this spread hump. Okay, we should expect a spike, just a sharp delta function like increase, jump here, because the condition is E equal to M, ECM equal to M, that is one particular value of ECM. But in observation, you see this bump, okay, with some width. This is because, so which I have written it here like this: though the resonance occurs at a particular value of the energy of initial particles, we observed a bell-shaped hump around this value instead of a spike. This is because the uncertainty relation, energy time uncertainty relation, you know, this is ET approximately equal to h cut. H cut is 1 in natural units. That means delta E delta T is 1. And this tells you that this much of amount of this energy, which is basically the rest mass energy, which is the mass in natural units, this delta E cannot be defined with an accuracy better than delta T. Okay, so delta T is the inverse of delta E, because this is 1. Okay, this is the reason you have a width. Is it clear? You have a width in delta M because delta T is basically the lifetime of the particle. Delta T is the however small it may be, 10 to the power minus 23 second. This is a small, this is not 0, this is a small lifetime. So within that small lifetime, the amount of E can be measured with this much of uncertainty, where delta E into delta T is equal to h cut. Clear? Because of that, you see a width in this. Okay, and this width is called, the inverse of this width is the lifetime of this process. And this is the reason the rate of this decay is called decay width. Width is this width. Okay, Is it clear? Okay, so this is the phenomenon of resonance. So if you, so suppose you are observing this interaction, and if we are measuring this cross section of the interaction, if you see that the interaction is like this, you must conclude that this interaction is not directly from A to B to C to D. There is some internal intermediate stage of this interaction where some particle has been produced, which again decays to C to D. Okay, so this is the conclusion. So this phenomenon of abrupt increase of this cross section is called resonance, and these particles, these short-lived particles, are called resonant particles. Okay, we will see there are many, though they are such kind of, they cannot be detected experimentally by observing their path lengths. Okay, because their path length is too small, too small to be resolved. In any interaction, even if in any weak interaction when happens, even if there is an intermediate particle which lives for a long time, you can see its path length. But if you see the cross section, you will see the spike, because if the intermediate state lives longer, you can see the path length. But then also you can see this spike because it is an intermediate particle. But only in that case, because its lifetime is much larger, then the width will be much smaller. Clear? It will be more spike-like. If the lifetime is larger, the width will be much smaller. Clear? Because this width or lifetime is inverse of this decay width. So this value of this, so experimentally, when you see such a abrupt rise in the cross section plot, you conclude that there is an intermediate particle produced, and the mass of the particle is the value of that energy at which this spike is observed. Okay, this bump is observed. Clear? Can I go to next slide?
Yes, sir.
Now the point is that even though these are very shortly lived particles, they are particles. They're an expression of energy in terms of material particles. Even though they are short, they are as good as particles like proton, neutrons, or any particles. Only thing is that the lifetime is short. Like elephant, tortoise, like highly lived animals are as good as animals like mosquitoes, or even some bacteria which have very few seconds of life, microseconds of lifetime. Okay, all are some expressions of life. So they have to be considered when you want to think of all the particles in nature. So these particles are there also. Now I will give you a list of all such particles which are resonant particles, which are observed as spikes in different observations, different measured cross sections of different processes. So this is a particle, this is a new particle, this is a new particle. Its mass is this mass, its mass is this mass, its mass is this mass. These energy values are the rest mass energies of this particle. Okay, their width is the lifetime of these particles. Clear? Nature allows these particles to exist for a short time, but they can be probed only through these resonance plots, these resonance curves. Here, have you understood resonances?
Yes, sir.
Yes, sir.
Like resonance, when you studied resonance in the context of oscillation, when there is an oscillating force applied to a oscillator of natural frequency omega 0, the force has oscillation omega. When omega is equal to omega 0, there is a maximum transfer of energy from this forcing system to the oscillator. So this is also when ECM is equal to m, there is this whole energy ECM is being transferred to in producing the particles. So they are called resonances, and we will study these resonances, their formula, relevant formulas when we study quantum field theory course. But this is the physics of this thing. Okay, let me clear this. Okay. So here are a list of some resonance particles, very shortly lived particles, which you see when you measure cross sections of different interactions, mainly cross sections of proton-proton collisions or proton-pion collisions. When you increase the energy of this collision and see plot their cross section, you will see many spikes. All these spikes are basically resonance particles, and you can say what is the mass of the particles because you know where this spike occurs, at which energy. That is the mass of the particle. And all these particles are given certain names, and these are their charges can be measured from their decay products, because resonance particles live very short time. They decay to products which are not resonant particles, which are long-lived particles or stable particles which can be detected. Okay, so these are the list for different resonance symbols for different resonance particles. Just have a look. There is nothing to understand it. Just this is a list. These are called delta delta particles. There are 4 kinds of such particles, delta plus plus. So okay, so there are some sigma particles, sigma star, 0 minus plus 0 minus, because sigma I have already used to denote some other baryons. So instead of using new symbols, we just introduce the sigma star. Similarly, chi star, like that. The thing you note that all the particles I list here are not their antiparticles. They have a different antiparticle set. Okay, and you can look at their decay lifetime, because lifetime is this lifetime is measured from the width of the bump. Okay, this width gives you their lifetime. Okay, this width of this energy, inverse of this width is the lifetime. And you see that all of them are this corresponds to a lifetime, which is equivalent to strong interactions. That means these particles decay by strong interactions. Okay, and accidentally we found that all these resonance particles have a spin, at least listed here, have a spin 3/2. So they are fermions, but not half spin. Their measured spin is 3/2. I will tell you sometime later how their spin is measured by measuring the spins of these products. Anyway, in a more complicated, more smart way. Okay. Now the thing is,
Hello, sir.
yes.
I have a question. In the first particle, delta double plus decaying to proton plus pi minus, each charge conserved.
Sorry, it should be plus.
Oh, okay, I understand.
There are many typing mistakes, because you know this typing these things is not, one can make many errors, and I am making it. Anyway, I will correct it. The charge is always conserved. Now I tell you, look at these decay channels, and from this decay, so this particle decays to this particle decays to this. From this decay channel, you can apply baryon number conservation, because baryon should be conserved, baryon number should be conserved, and you know the baryon number of the particles produced in this column. Okay, all the baryon numbers are now known from these previous classes. From that, you can calculate the baryon numbers of these particles. So P and pi, so lambda plus plus should have a baryon number, how much? +1, because P has a baryon number +1. That means this resonance is a baryon. It is a resonance, but it is a baryon resonance. This resonance is also a baryon, because N is there. So baryon number 1, pi is 0, so it is 1. Similarly, you can check all these has baryon numbers 1. So you can check that all have baryon number 1 and all have spin 3/2. You can measure it experimentally. Now, see that all these interactions are strong interactions because their lifetime is so. And we have seen that strangeness is conserved in strong interactions. Therefore, strangeness should be conserved in all the decays because all of them are strong. Therefore, and since you know the strangeness of these particles, decay products from the listing of strangeness per strange particle tables shown earlier, you can also calculate the strangeness of these resonances. And you can check that strangeness of delta should be 0 because none of them are strange particles. Here, there is these sigmas, these particles are produced. So all of them have strangeness -1. So sigma has a strangeness -1. You can see the sky is produced with this decays to this particle. So chi, this is a star chi, this is non-star chi. This non-star thing has a strangeness -2, we have seen. Therefore, it has a strangeness of -2. This is a strangeness column. Okay, so strangeness is like this. That means, and we have said that any particle with a non-zero strangeness is a strange particles. That means these resonances all are strange resonances which have a strangeness -2 or -1. So I marked them with red. I forgot to mark it with red. It should be red. Clear? So these are resonance particles, but they are all of them are resonance baryons, and all of them are strange particles. Sorry. Besides these 4, others are strange particles. They have strange 1, -1, or non-zero strangeness. Only this 4 has 0 strangeness. Clear? This is, so we are exploring more and more about particle zoo. After we have explored to a certain point, again we will extract the pattern or symmetry in that particle zoo in terms of some simple sentences. We'll see that, and that we'll see that gradually. There are some, and this is an incomplete list. You see, this is an incomplete list of baryon resonances. Similarly, there are other resonances which are denoted by these symbols. These are their masses, and these are their decay products. And you can check their lifetime. Most of them are strong. This is also strong. One channel is electromagnetic. So far as decay modes are concerned, I have only mentioned the prominent decay mode. There are other decay channels, but this is the decay mode written here, has the maximum branching ratio. Okay. Now here you can also check, if you check these particles that calculate the baryon number, you will find that baryon numbers of these resonances are 0. All these particles are 0. That means these are mesons. Resonances, but mesons. And you can check that since the interactions are strong and electromagnetic, strangeness should be conserved. So you can also calculate the strangeness of this particle since you know the strangeness of all these decay products. And from this you can check that strangeness of S is this. Strangeness 0 is for this rho, phi, omega. This is 1 for this, -1 for this. So these are K star things. Okay, different from K mesons. This is an resonance K particles. Okay. So the 2 points to note here is that in this list of resonances which are baryons, I have listed only particles here. There is a different antiparticle set because delta plus plus has its own antiparticle. Delta plus has its own antiparticle, and it is not delta minus. Here, it is just a symbol. The different symbol I used, but its antiparticle symbol is never used in physics because we don't need to, if you know the particle, we automatically know their antiparticle. All of them has opposite quantum numbers. But delta plus and delta minus, remember, they are not antiparticles. When they are, for baryons, we adopt these notation. Okay, but when they are mesons, I have put both particles and antiparticles here because rho plus and rho phi, they are particles and antiparticles. They have same mass. Rho 0 is another particle which is zero charge, neutral. It has this mass. It's slightly different from the above, but it is its own antiparticle. So its antiparticle is not in this list. It is in this list. In other words, it is in the list itself. Omega phi are also neutral particle. They are their own antiparticle. K plus, star plus and K star minus, they are antiparticle of each other. And these two are antiparticles of each other. I give a star mark here in the decay product of this K0 and K0, K star 0 and K star bar, because to understand this, their decay products, we need to understand something more. I mean, the more physics is involved, which we will discuss later, because these K particles are something, some unique particles. They exhibit some extraordinary features, which we will see later. They are called kaon oscillations. Okay, we will not discuss it here. So note that from all the decay modes, all these above particles have zero baryon number, so they are mesons. They have lepton number also zero. The table contains both particles and antiparticles. And also note that rho 0 omega phi, these three particles are particles which are something which have different masses, but all of their other quantum numbers are same. Their B's are zero, strangeness is zero, their lepton number is zero, their charge is zero, their spin is, oh, by the way, their spin is one. All of them, all of the mesons of these resonance mesons are found to have spin 1. Okay. The earlier mesons, like pi mesons, K plus mesons, they have spin 0. Here. So we entered into the particle zoo a little bit more and found more and more resonance particles, out of which some resonance particles are baryons, some resonance particles are mesons. Here, this is the bottom line. So basically, we enlarge our list of baryons and mesons. Okay, some of them are very short-lived, which we specifically call resonance particles. But if you drop these idea of, if you don't look at their time, their decay, their lifetimes, there are just many baryons and many mesons. So this will not. So let's stop here. But before stopping here, let me give you a list of all the baryons and mesons we have here together. So this is you can check, this is a list of all baryons. This proton, neutron. I have written only their masses here only for a different reason. These particles. Now these are the resonances. This delta, this sigma star. These are different from this. Okay, all of these three are also sigma. These three are sigma stars. They have different masses. These are this. Similarly, for mesons, we know this pion, their masses are given. We have written this, but here we put particles and antiparticles in the same column. Here only particles are put, their antiparticles are not put here. Okay, so this eta, it's on depend, eta prime, rho 0, omega phi, etc. Now, if you give a careful look at their masses, you will find, now forget about everything and look at just their masses. So we have discovered baryons and mesons from nature, which nature allows to exist, even for however short time it may be. Okay, some may be stable, some may be shorter time, some may be much shorter time, some may be much shorter time, depending on the decays by electromagnetic weak or strong. But if you look at their masses, you will find this feature. Some of the particles have very close masses, like proton and neutron. They have very close masses. Like this sigma particle, they have very close masses. Here, these three are close. These two are again very close. These 4 are again very close, so close that I have just written their values within this error bars. I am not sure what is the exact value, but their value lies within these values. All 4 have different masses, but within this range because they are so closely packed. So these are again masses, closed masses. These are again closed masses. But there are some particles whose close companions are not found. Okay, like this. Similarly, in this meson table, you will find these pions have very close masses. All these K mesons have very close masses. Eta is singular, eta prime is singular. These rho mesons have very same masses, almost same masses. Omega is singular. This phi meson is singular. This again K star mesons have very close masses. Okay, so this is again a new type of pattern you find in the masses of them, and this is not random. Okay, so if you look at the mass axis, you will find there are protons and neutrons here. Again, pions are below. Pions are three close masses are here. Like there is 1 lambda 0 here. Then 3 sigma masses are very close. Okay, now 2 chi masses are very close. They are ordered up, they are not arranged in ascending order anyway. Now there are 4 particles, four delta masses are very close. So you see this pattern in these masses. So since this is a pattern, this is not random, there must be a reason for this. Or we will see whether we can find the reason for this. Okay, so next day we will introduce the concept of isospin introduced by Heisenberg, with the help of which we will understand why these particles have these masses. And this we will see that this will prove you that these near masses of these groupings of masses of these particles will ultimately lead you to the fact that they are not fundamental particles. They have some constituents. Okay. So let me stop here. So, sorry.